Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We had been discussing river water chemistry in our previous lecture, and in today's lecture we are going to discuss some more. So, we have stopped in this particular junction, and we had been discussing how the river water chemistry is so complex, and there can be inputs, there can be organic processes, there can be inorganic processes that are all happening simultaneously and continuously to give us an understanding of what we are, what is happening. And when we work with such complex systems, we need to have multiple tracers, multiple data sets to be really be able to understand how complex the system is. And most of the time having concentration data is just not enough. Okay. Therefore, the importance of isotopes in such cases, and for such complex systems, when we are targeting certain processes, we can have specific isotope systems that targets the behavior. For instance, if we are looking into clay orthogenesis, we can look into lithium isotope systems, because lithium isotopes is very well fractionates specifically with respect to clay formation. If you are looking into legacy sediments, if there is a problem of legacy pollution there, then we most likely would use our sediment data. We can use sequential extraction of sediments, and we can see that which phase of the mineral is more contributing to a particular element, and how is that relating with the natural conditions. If we are interested in more of the biological interactions, we can use isotope systems that that indicates more of biological interactions. So, maybe iron isotopes or zinc isotopes. So, they maybe help us, or combining them. So, iron, zinc, they both of them simultaneously we can use, or if something is coming absolutely anthropogenic, we can use lead isotopes. If something is coming from groundwater, we can use a groundwater tracer, we can use weathering tracer. So, weathering such as strontium isotopes, neodymium isotopes, these are specific isotope systems that can give us information about the about the weathering system. Anthropogenic, we can look into lead isotope system, it will give us a lot of information there. Okay. Plus, in additional, we definitely would like to see water isotopes, because they help us understand how much is coming from rainfall and groundwater. Okay. If the water itself looks like as if it is dominated by groundwater supply, then the water isotope data itself will show that. Okay. So, not only a lot of concentration, but the isotope systems is immensely useful in these kind of aquatic systems, understanding such kind of complex systems. Now, when we look into river data, how does a river data look like? I am going to show you an example of the data from the Ganga river. This is the river that I studied during my PhD. And in this figure, I have plotted only 4 elements, and these elements are very specific. So, we have vanadium, we have copper, we have chromium, and we have rubidium. And what I intend you to show is the kind of variability that comes with all the elements. So, vanadium's plot is very different from copper. Copper and chromium are still look similar, but rubidium again is very different. Okay. So, here vanadium in the, so this is starting from upstream. So, at very mountainous regions. So, this is close to Harshil location in the Bhagirathi river basin, and as it flows down meets Alaknanda, Devprayag, and then flows down. So, Rishikesh, Haridwar, and then again comes to Kanpur, then again flows down and all the way up to Farakka in West Bengal. Okay. And in between There are other tributaries joining in. There can be Ghagra, there can be Son, there is Gandak and there is Kosi. So, all these are large tributaries of the Ganga that comes and joins in, okay, and they are again large rivers themselves. Okay. So, therefore, Ganga is a huge complex system, but this data is of only the mainstream Ganga. This does not shows the Ghagra, Gandak, Kosi data. So, this is just the mainstream as it is evolving from the Himalayas, okay, to the Bengal delta. Okay. And this is not close to the delta, this is where the river enters Bangladesh, and we have no longer entry into the river. So, this is the point which is called a place called Farakka. Okay, that is the place where the river enters Bangladesh. So, that is the last point. Okay. So, how vanadium, so as you can see vanadium here is increasing. So, it is very stable in the mountainous regions, okay, it is very stable in the mountainous regions, and as it is going downstream, slowly it increases. A very sharp increase comes here as soon as we move from the Himalayan catchment to the Ganga floodplain. After the Ganga floodplain, we have a huge jump, and this particular location with the very famous the Allahabad. Okay, this is the Allahabad location where the composition of vanadium is very high. Okay. So, this kind again it goes down again, and again it gets very stabilized. Okay. So, what is happening here? So, this particular zone, why is this highlighted? This zone is highlighted because this is the stretch at which most of the pollution is known. So, this is the stretch known from just from Kanpur to Patna. This is the stretch, and this is called the middle stretch of the river, where the river is known to be very polluted. Okay, where the river is known for its continuous inputs coming from a lot of industries. There are big anthropogenic hotspot areas like the cities, Patna being one, Allahabad being one, Varanasi being one, so Kanpur itself being one. So, a lot of cities are there in this particular region, and of course, therefore, a lot of industries is also there. So, a lot of waste is getting dumped in the river. So, how the river reacts? How does it change from value which is very close to 0 to it gets almost several times high at severely polluted locations. And is this true for all the metals? No, it is not true for all the metals. For all the metals we have different types of plots. So, as we see, this is the spatial plot, how the river is varying spatially. So, when I when we discussed about sampling techniques and all, we said that when you sample a river, you do it spatially and you do it temporally, or you take at one particular point and you do for a very long time. So, that is like a time series, you are doing it every day, you are doing it every week, you are doing it every month. So, that is like a time series. So, this is more of a synoptic sampling, that is was done only for a 1 year for 3 seasons, but it was not repeated continuously. So, one pre-monsoon, one monsoon and one post-monsoon data, and that was averaged out. Okay. So, this is that kind of data set that we are looking at. Okay. And this is because it is a huge geographical area to cover. Okay. So, often when you have a big when you are looking into catchment scale, then having a time series becomes very difficult. So, such kind of data is more of the synoptic, but seasonal, at least seasonal has to be maintained, at least one monsoon and one non-monsoon, because these rivers are extremely different during those 2 times. The monsoon and the non-monsoon periods will look very different. Okay. So, whenever you are looking into a river that is very dominated by the monsoon, by the hydrograph, then you need a sample which represents a dry flow condition, and you need a sample which represents a very high flow or high stage composition. So, this is the plot that we see with respect to vanadium, copper, chromium, rubidium. Let's see, let's just talk how the different elements are. So, copper and chromium, they behave more or less, more similarly, even if not absolute mirrors, but they are much, the trend is much more similar. So, chromium is very low, very high again in the in this middle patch, and again goes down. Similarly for copper, okay, and at this particular location, that is this DS4 location, vanadium, copper, chromium, all of them are very high. Rubidium as comparison is a very different element. Rubidium is more of a geogenic weathering tracer. Okay. Rubidium is more coming from the continental crustal weathering as compared to anthropogenic mobilization. Rather, copper, chromium, these are anthropogenically mobilized elements. That means, they are not there in natural weathering, or they are there in the weathering system, they will be released, but their mobilization is far low, as their concentrations are far low as compared to rubidium's mobility. So, rubidium is a very soluble, very mobile, and is a very high concentration even in the continental crust. And as you can see here, that even in higher in the Himalayan regions, its composition is very high, and it is completely comparable to the downstream locations. In fact, the downstream locations, rubidium's average composition goes down, right. The average composition in the upstream is higher as compared to the downstream locations, and significantly lower, significantly it gets diluted in the downstream locations. That means, weathering is low, anthropogenic pollution is high. Okay. So, that kind of system is this kind of system. Okay. Similarly, when you see here, copper very nicely shows this. So, this is a plot showing the different regions. We have the headwater that is very close to the glaciers. We have some points there, maybe 50-60 kilometers downstream of the glacier, that is basically the proglacial zone. So, we have the headwaters there, we have the upstream, okay. Then we have, following the headwater, we have the upstream catchment of the river. Then we have the downstream catchment, and then at this particular last location, we have what is called a time series. That means, every month our data was collected. So, we have for a year, we have all the month data. Okay. So, this is one particular location. Okay. This is from one location. This is called the time series data. So, this is for copper and this is for rubidium, and this graph clearly shows how rubidium is such a specific tracer for continental crustal weathering, okay, where the headwater and the upstream and the downstream has very similar and comparable concentration ranges, even though the concentration ranges are very varying, okay, but it is comparable and there as compared to the copper, which clearly shows the kind of increase in its concentration as we move from the headwaters and the upstreams to the downstreams. Okay. How it goes, how it gets increased multiple times as compared to the headwater and the upstream areas. And finally, before it before it joins or flows to the delta region, the flow of the other tributaries, the Ghagra, Gandak, Son, Kosi, these rivers, when they come in, the composition of the particular elements, they can come down. Okay. These high concentrations, they are not consistent after these large tributaries after they join in. Okay. So, very important kind of information that we got, and what kind of is this when we talk about data sets. Therefore, we make it our sampling biasness or whatever. We call this a kind of sampling biasness indeed, because from our synoptic sampling, there can be something which is like moving continuously like this. But when we are going for sampling, we are just sampling one time. So, this is one day, this is day 2, this is day 3, and again sometime in here we are again doing. So, we do not know what happened during this time. Okay, we do not know what is happening. Okay. So, this is the difference between continuous and synoptic sampling. So, for rivers, it is very if you want to study it really well, then it's might be necessary to have one particular location where you are continuously recording the data. Okay, because that give us much more information of why rubidium is behaving like this, why chromium is behaving like this, rather than saying this much is coming from weathering and this much is coming from weathering. Am I able to show the entire complexity that is seen or expected of a natural system? Okay. For that we need to very well understand something called the CQ relationships. Okay. That is, the concentration stands for C and Q stands for discharge. Okay. Very complex system. These catchment scale understanding is very much required. That is because when rainfall is happening and flow paths are getting activated, different regions in this catchment, they are facing different kinds of weatherings. The signals we are getting from the different regions may differ. If you are looking into Ganga, okay, then there are different tributary basins, and the different tributary basins have different kind of lithologies. Their flow paths will be different, their reaction pathways will be different, their weathering patterns will be different. So, during the evolution of spatial scale and temporal scale, the way they contribute to a final point, for instance, you are taking this point as your final point, will be very different. Okay. So, when we are looking into river data sets, it is much important that we have continuous data sets, and what we have is also not only the chemical reactions, we have something called the hydrological transit time. That means how much hydrology will contribute to controlling the paths, how much time will it be available for the water rock interactions to happen. Okay. It's both physical and chemical. So, there will be physical laws and there will be chemical laws. Okay. Both of them are happening. Okay. There has to be you will have equilibrium reactions, you will have kinetic reactions, all of them will merge to what you get, what you see. Okay. To understand that, you need much complex catchment scale models. Okay. When we look into the critical zone, we look into complex systems, we need to understand how this entire catchment scale modeling is happening, right. And this kind of models, they take into consideration thermal thermodynamics and equilibrium reactions and kinetic reactions, okay, and along with the hydrological time scales, how much of the C is explained with the Q. Okay. And you can refer back to all these very interesting papers that has coming out related to these studies. And now what we see is called these concentration discharge relationships. So what happens is, the discharge definitely controls the concentration. Why? Because when the concentration is very high, okay, then there can be a dilution effect. When the concentration, when the discharge is very low, then we can get naturally very high concentrations. So, changes in the flow rate or discharge is accompanying the changes in its water quality. During the dry periods, there is more contribution coming from the groundwater or the base flow to the river chemistry as compared to the wet season, where there is the overland flow, whereas there is more rainfall, there is just a lot of dilution. So, when we have this concentration by discharge plot, we get to see three kinds of plots. Okay. So, the first kind of plot is this, that is, with the increase in discharge, the concentration decreases. Okay. With increase in discharge, the concentration is decreasing. That is a simple dilution line, that is C is directly proportional to 1 by Q, inversely proportional to discharge. Concentration is inversely proportional to discharge. But what we also see, that most of the major cations and the major anions, they follow such plots. So, here you have the silica, the calcium and the sodium, and here you see that there is a slightly slope, but it flattens out, it flattens out here, it flattens out here, it flattens out here. It does not follow the straight way simple dilution curve. Why do we not see that simple dilution curve? Okay. The reason is that when there is a lot of increase in discharge, the concentration of the these elements are also rising, because it is getting released from different kinds of reactive zones, either that is coming from more weathering. So, weathering also increases with discharge, weathering also is increased. Okay. So, that weathering is releasing this concentration. So, it is not a simple dilution that I am observing, it is rather an enhanced weathering that I am also looking at. Okay. So, CQ relationships have now helped us understand how different different elements can behave differently. For instance, silica, one instance, silica here in this particular data set, you can see the very sharp decrease in its concentration as the discharge increases, and it is a simple dilution trend, more or less a dilution trend. Okay. As compared to this is phosphorus, with increase in discharge, concentration is increasing. We were expecting a dilution, but no, there is more sediment interaction. The more sediment bound phosphate got released during the during higher discharge, and such examples happens not only with the more sediment bound particles, but also with changes in physiochemical conditions such as pH and alkalinity in streams. So, heavy metals they can sometimes show such kind of behavior when there is a lot of inflow of different kinds of materials. So, discharge is increasing and the concentration is also increasing. Okay. So, there is a rise in the concentration with the discharge, which shows that some kind of condition has changed, prevailing condition has changed, or the sediment bound particles has now moving into the dissolved phase. And when we are going to look into mixing of waters, okay, then this equation is very important. Okay. The water quality and quantity, they are inherently interdependent. The amount of water that is passing through at a particular point definitely imparts the quality. Okay. When we are going to understand this, we need to employ more conservative traces that follows this kind of equation. That is, the addition, this final concentration is the sum of the concentration into discharge of the source contribution. So, if you are looking at chloride, for instance, which is the most conservative tracer, then if you are saying okay, this is coming from rainfall, okay, this much amount is coming from rainfall, or this is from a particular tributary. Okay, so this is tributary A, this is tributary B, okay, or this is some other source. So, we are going to use this kind of mixing equations, where the concentration into discharge is equal to the concentration into discharge of the individual sources. Okay. And it is not only this, these kind of models now has been transmitted to what we call the reactive transport models, okay, RTMs. What does the RTMs have? The RTMs have not only have the reaction times, okay, the reaction times required based on the thermo and the kinetic principles, but also it has the flow path timings, the flow paths, okay, how much time will the flow path allow. Okay. So, the flow path and the reaction times, all of this gets combined in these kind of reaction transport models, and we are able to understand. For instance, what we see here is something called the transit time distributions, and what we are trying to do is we are trying to understand how the water is moving through a given a system. For instance, this is a transport column. Okay. This is a this is a imagine this as a soil section, or that is soaking in water, that is taking in water. Okay. So, the water is coming in here, there is a flux of water that is entering the system and it is getting stored, it is getting stored into the system. Now, what kind of distribution is causing its release into the runoff? Is it water from all the depth that is releasing to the final runoff, or is it water only from the more? So, water is entering here, it is getting pushed down, and the more of the water is coming from the old water, or is it the new water that is going more into the runoff, while the more aged water is contributing least. So, this kind of variation we need to understand when we look into the CQ relations, because that is what is going to help us in understanding, okay, whether it is going to be something like this or this or this. So, whether it is going to be chemostatic, whether it is going to look like a dilution, or it is going to look like an enrichment, and why does it look like this. Okay. So, this is just like a physical analogy of the storage system in a particular basin, where there is water that is getting injected at a particular rate, and that is displacing the water downwards. Okay. Thus, ST is the storage. Okay. This is the storage age, okay, related to a particular water, and that is slowly going out as it is discharging. So, the question is which water is getting discharged into the system. A physical analogy is here presented again. So, imagine this is a dry period. So, very peak summer season is there. As soon as there is precipitation, it goes it goes into directly, it can go through the soil, it goes through the the leaf system and the tree system and everything. It gets stored into the soil layers, it gets stored into the soil layer. That again preferentially goes down to the groundwater, gets stored into the groundwater, and there is some flow into the river, which is coming out as stream flow. So, during that time the stream flow is dominated mostly by this old groundwater and only a little bit of this new water. But imagine it is the monsoon has come and it is the wet system, it is the wet period, and all of this soil and land whatever is there already is very wet. Okay. So, there has been a lot of percolation already. So, the precipitation comes, there is also mixing, but there is also release. Okay, there is also a lot of mixing and release, and the amount that it goes in is very high. The amount that goes directly to the groundwater now is very high, and therefore, this new water that is coming as through the precipitation is also coming into the stream flow. Therefore, now the stream has a lot of water as compared to the beginning of the dry period. So, after the wet period comes again the dry period, again the top layers of the soil has returned to its dry state. Now, mostly it is just the groundwater that is going and filling up the rivers. So, this is a conceptual again schematic showing the dominance of groundwater dominated flow during the dry conditions where the old groundwater is coming in. Then there is the wet conditions that rapidly expose the young water coming in, as compared to the beginning of the dry season where this new groundwater and the more mixed groundwater, okay, this groundwater is coming. Okay. So, you can read this particular reference Rashevitz et al 2016 that talks about transit time distributions, because it is a very very interesting paper related to the transit time distribution in natural systems and how it controls the CQ relationships in different different kinds of systems. So, therefore, when we talk about rivers, when we are working with natural systems, we have to work with a lot of problems, right. We have to work with effluents, okay. We have to work with the dominance of direct waste, okay. Direct waste entry. We have to work about huge population. Then we have rituals, then we have encroachment directly on the water systems. So, this is a bridge that is being created on the river. It is a direct impact on the water body, because a lot of construction materials are coming in continuously. The the ecosystem is having a lot of pressures with these dust and construction materials that is going on. So, the river bed, everything is shaken up at this point. So, this encroachment, this kind of construction activity is a huge threat to the rivers, and of course, bathing and washing and everything that is going on, a lot of waste is coming in. Okay, something you may not even understand, but these flowers and everything, they are all releasing something. Okay. So, there is not only abstraction, okay, there is not only abstraction of water for different purposes, these are other threats that controls the river water quality. Now, when we talk about river water quality, what we also need to know is that where are we comparing this data with whose data are we comparing it. So, what we need to find out is the background water quality. Okay. When we compare, we often compare it with drinking water. Okay. So, this particular river has a chromium concentration of so and so, and it is compared with the drinking water, but no, the river is not supposed to flow with water that is of drinking water quality, right, because natural weathering processes is giving out this concentration, the solutes are coming from weathering plus anthropogenic sources. So, what we rather need to find is the background concentration, how much concentration is there in the groundwater, the upstream water, that will help us have this background water quality. Now, how do we find that background water quality? We have to either find specific formations where the weathering is very high, okay, which is most likely controlling the composition of the river, okay, and such that it is not close to a human stressed human modified area. So, far from human activity, more and more natural. So, either find the data from that area and say, okay, this kind of water is dominating the system, okay, or you find it out from the other water bodies, the lake water, the groundwater have the entire basin scale done. So, those are more pragmatic ways. Okay. So, naturally the groundwater is so high, the river is like this. So, the ambient background is like this. So, the water is of this quality. What is the usefulness of this kind of ambient background quality? So, when we are having this, we are comparing the river with itself. We are not comparing the river with a rock or with a drinking water. Now, what is drinking water? Drinking water is the water which, if when we drink, we are not going to get any kind of sick or disease. Okay. That is basically depending on our removal process, our metabolic processes. Okay. So, that has nothing to do with the river water quality. Our determination of quality is somehow being pushed into a sense that whatever is only suitable for us humans, if it is fit for use for drinking or bathing or for whatever reasons that we see, if it is only fit for us, then it is good quality. No, the river naturally has a quality. What we need to find out is what the natural river water looks like. Then only we will be able to know that whether the river got polluted, whether the river is at its tipping point, whether the river has a healthy ecosystem, yes or no. Okay. So, this is the this is a plot showing the background water, this is the ambient background water concentration for the Ganga river and compared to the global river average, and this is the WHO standard for drinking water. And as we can see that the Ganga average river water composition is lies very similar to the global river, or is basically it is suitable and okay for the Ganga itself, and this kind of data set will help us understand whether the water has declined its quality in the future. So, when you are going to take a data set 10 years down the line, you will know, okay, this was the quality 5 years ago or 10 years ago, and this is the quality now. So, clearly the river has degraded. So, such kind of background water quality data is required to know whether the quality has degraded, okay, or not. With this, I come to an end to this lecture, and we are going to discuss another system in our next lecture. Thank you.